Hello and welcome to the second lecture for Research Methods 2, which is about quantitative methods. This lecture will be online again by popular request by many of the students who thought that they would prefer online lectures rather than face-to-face lectures all the time. This is kind of a lead up to future developments for this course where I want to create some online clips with shorter mini lectures rather than one. This is just the old style because it takes a lot of time to prepare those materials, and this is just a full lecture as one thing with just the PowerPoint slides that we would otherwise use. The PowerPoint slides will also be available on Student Portal as the other materials will be. So the first lecture is going to be dealing with a couple of things. First, we'll go into a quick review for all of the stuff that we've learned in Research Methods 1, just to see if we're all on the same page still. Then we'll move on to associations between two variables. So we've talked about correlation already, Pearson's R. We'll talk about a couple more because Pearson's R has its limits and its specific use cases. After that, we'll talk about multiple regression analysis. So we've already talked about regression analysis. But we haven't discussed completely how that works if we add more independent variables, so more X variables. After that, we'll have a little bit of time that we spend talking about quality control in statistics and in quantitative research. And finally, we'll talk a bit about factor analysis, which is a more advanced technique, like regression analysis is, but it has different purposes, different use cases, and it might be helpful for some of the students. All of these things will come back in the lab session that we have in this course as well, but there we'll bring them into practice. This particular lecture deals a bit more with the background, the theory, the reasons why you might want to do these sorts of things, and the lab sessions focus on applying this rather than the theory behind it. Let's go into our quick review first. In Research Methods 1, we've talked about significance level and how we might test hypotheses. So we've talked about how p-values can be distributed, values can be distributed along a normal curve and what the p-value represents there. So the p-value can take different numbers, right? So in our case, SPSS gives that to us. It could be any other program that does it for us. You could calculate this by hand, which is not what we're doing in this course. We're not concerned with that. But in our case, SPSS gives us the p-value. Common examples that people work with for relevant p-values are p as 0.1, p as 0.05, or p as 0.001. And these correspond to our alpha values that we set. And the way this works is that the p-value is the calculated value. In other words, how unsure are you about rejecting the null hypothesis? And our alpha values represent how unsure we want to be. So this is not a calculated value, this is just the bar that we set for ourselves. And so why you might choose higher or lower alpha values is relating to different ways of doing research, different types of research specifically. So this relates to the size of the sample, but also what your research is about. So if you're doing medical trials, you want to have a very small alpha. You want to be not so very unsure about rejecting your null hypothesis. Whereas if you're doing more vague studies like sociology of religion, let's say, there you might get away with doing an alpha value that is 10% or sometimes even 20%. You see that published. In any research, though, the lower the p-value, the more sure you are about saying that there is a significant effect. So when we're testing hypotheses, we start off with saying we have a null hypothesis, and that is the one that we are really rejecting, right? Remember Popper, if not, go back to Research Methods 1 slides and see what we talked about when it comes to Popper or philosophy of science. We'll go into this, I'm sure, as well. And what we do when we're saying that we're testing hypotheses, basically just comparing the p-value that we get to the alpha that we've set. And then we say if the p-value is smaller than or equal to alpha, then we reject our null hypothesis, and then within parentheses, we accept the alternative or research hypothesis. This doesn't mean that the alternative hypothesis is true, it's just more likely, just because we've disproven, we falsified that the null hypothesis would be true. So before we go into further details, I want to recap on the nominal and ordinal interval and ratio that we've talked about before. This will come back in lab session again. So here in this overview, you see how data might be measured. So data at the top, we have categorical and quantifiable types of measurements. And then within those, for the categorical, we have nominal data or ordinal data. And for quantifiable, we have interval and ratio. SPSS calls both of those scale in its program. It doesn't distinguish between interval and ratio because those are mathematically the same. They don't work in any different way. They don't require a different type of method of dealing with them. So SPSS doesn't distinguish. We do though, because for a survey design, it might make a difference, or for the way we set up our experiments, it might make a difference. So to recap, I have a couple of examples for you. When we are measuring something specific, we could measure that in different ways, and they would be nominal, ordinal, interval, or ratio. So let's take the variable age, how old someone is. A very typical approach that you might see in surveys is something like this. We have different groups of ages, 20 to 24, 25 to 29, 30 to 34, etc. And people are supposed to just tick the box that best describes them. In my case, that might be the group that is missing, I see now. So that's 35 right now. For you, that would be the first group mostly, I'm assuming. Yeah, but it might also be a missing group here. Disregarding the missing groups here, this would be an ordinal approach to it, right? We get an ordinal measurement for age. We have groups of age brackets, but we don't know exactly how old people will be. Usually a better approach would be something like this, which is also simpler in this example, which just says, please state your age. I'd say 35 for me, that for you maybe that's 19, maybe it's 20. Or we could do something like this, please state your date of birth. So 1983 for me, somewhere in the 90s, I'm assuming for most of you. Either of these measure age in the same amount of precision, even though please state your age will give us a ratio measurement, right? Because it starts at 0 at least. We can't have negative 5 years old. And please state your date of birth would be interval, because we would get a year of birth. And there is a year 0. Hypothetically, someone could be born in that year, but we also have -7 or -20 or 200 BC. Right? Those would still be valid dates if we were doing historical research, for example. So we see how we have 3 ways of measuring the same exact thing, but they result in different variables, right? The measurement types. So we have ordinal, we have interval, and we have ratio. We could measure age, I suppose, in nominal measurements, but that would just get weird very quickly. I'm thinking something weird like, what's your age? Choose a color, right? Which sounds a little random, but maybe if you ask people to describe their age in terms of a category that has no order, like color, right? So maybe gray is associated with old people, maybe blue or green or red is associated with youth. I don't know. It's a little strange, but the point here is the overarching point for this is nominal, ordinal, interval, ratio do not refer to what we are measuring, in this case age, but to how we are measuring it. Yeah. Okay, so next I'd like to move on to measures of association. So this all refers to how 2 variables correlate, right? How they go together. If one goes up, does the other go up? What happens to the other one? Yeah, always 2 variables. And we've talked about this before. We've talked about this before with our old friend correlation. So correlation works for interval or ratio variables. It works with variables that have some certain characteristics. We'll get into that a little bit later as well. But the most common notation for correlation will be Pearson's R coefficient. And as you remember, it takes the form of these types of scatter plots, where we have any given variable on the y-axis and any given variable on the x-axis, and they associate in some way. So you see the pattern here represented as dots, as being data points in these different scatter plots. 0 would be no correlation whatsoever, just a random fluffy cloud of things, and +1 and -1, absolute 1, will be a perfect correlation. So if you know the value of variable x, we are certain pretty much about the value of the variable y. We can predict them one-on-one. We can have higher correlations. That this is just how this measurement is scaled. And then in between 0 and absolute 1, this is where basically all the relationships will fall, at least outside of the natural sciences, where we might find +1 and -1. But even in the natural sciences, that's only applies to specific topics, of course. 0.4, 0.8, and anything in between those things. So we've talked about these already before, so let's skip ahead to our alternatives. So the problem with this is correlation works with interval or ratio variables. So what if you have nominal variables? With nominal variables, we'll have to use something different. We have a couple of options, and I'll put them on screen here. We have the chi-square, which has no indication of strength of the relationship, and we have Cramer's V, which does have that. It ranges from 0 to 1. Here's a rule of thumb where literature shows that 0 to 0.21 is very weak, 0.1 to 0.25 is weak, all the way up to very strong, which is anything over 0.45. 1 is still the maximum for Cramer's V. So you don't have to necessarily remember when you would use either. The general description here would be that the chi-square is just an older measure for doing this, and it's lacking in the way that it can't express strength, not very easily at least. What it does do is tell you, is there a statistically significant relationship between variable x and variable y when they are nominal variables? Cramer's V is really just a standardized version of this chi-square, so it tells you both is it significant, yes or no, or what is the p-value, right? Works the same way as in the other analyses that we've had. It gives you a p-value, and SPSS calls that sig dot for significance. But Cramer's V also tells you how strong that relationship is then. So what if we have ordinal variables? For ordinal variables, we have a couple of options, specifically Kendall's rank correlation, which they call tau. This ranges from -1 to +1 as well, like Pearson's R. And we have two types of tau, tau B and tau C. You'll find both of those in SPSS when you go looking for them. Tau B for square tables and tau C for rectangular tables. I'll get back into that in the next slide, but it's not so very difficult to distinguish between the two. So Kendall's rank correlation, and we also have Spearman's rank correlation called rho. So this also works in a similar way. I'll get into how they are different and how they are the same in a bit. But here we have first a square table, right, with 5 categories on the rows and 5 categories on the columns. This is what makes it square. It's symmetrical. So tau B. And here we have a rectangular association table, so it's asymmetrical, right? We have 5 categories in the columns, and then we have 3 categories in the rows. So here we would use tau C if we were inclined to use either of those. We could also use Spearman's rank correlation. So to illustrate how this works is both the chi-square, Cramer's V, Kendall's rank correlation, and Spearman's rank correlation, they have a particular way of working that is different from Pearson's R. So Pearson's R has a calculated value, much like the y equals a plus b times x that we've seen in regression analysis. So it's pretty similar to that. When you do correlation and you get the coefficients, you'll see that they are pretty similar to what we find in regression analysis. So there's a similarity there. This is because they have similar assumptions to the data. It has similar requirements for the data. Not the nominal and ordinal variable associations, chi-square, Cramer's V, Kendall's rank, and Spearman's rank. Those work by looking at what we might expect in a cell, in any given cell, so where a row and a column intersects, and what we actually see in the data. So for example, if we have a 2x2 table, very simply, we would say, and we have 100 things that we're observing, 100 people that we're observing, let's say. So if the null hypothesis would be true, there would be no relationship between the two variables, right? So those 100 observations would be equally distributed in terms of what they score between those 4 cells, 2 by 2 table, right? So in each cell there would be 25 people out of 100, a quarter for the 4 cells. So this is what's called the expected cell count. And so the expected cell count is then compared to what we observe. So the observed cell count, the actual thing that is in the sample that we've gotten. So perhaps in our sample that we're imagining right now, in those 4 cells, there's 40 people in cell 1 and 40 people in the last cell. So in a diagonal row, we'd get 40 and 40, which leaves us with, 10 and 10 in the other 2 cells, right? Out of 100 people that we've had in the sample. And so what all of these measures of association do is then look at, is the observed cell count in this particular cell significantly different from what we might expect based on the null hypothesis? Yeah? So is this different from what we might expect based on the null hypothesis, which states no relationship, therefore an equal number of people in each cell, equal number of things in each cell? If so, yes, it is statistically significant. If this happens with enough cells, this will make the bigger measure, so the chi-square, Cramer's phi, Kendall's rank, or Spearman's rank, significant. And this has a couple of advantages. One is that it doesn't require the relationship to be linear, right? So if you have a cell table that is bigger, like the ones that we've just seen, the square and the rectangular association table, we could have a pattern that follows a curve or just applies to some cells but not others. It doesn't have to be linear across the board. This would be the case with regular Pearson's R coefficient. It assumes a linear relationship, a straight line. So does linear regression analysis. But we won't get into different types of regression analysis in this course, but they do exist as well. So for measures of association, this is how they work, and it makes it a little more flexible. At the same time, it makes it a little difficult to interpret compared to Pearson's R coefficient. So when we have interval or ratio variables that are linearly related, more or less, we tend to use Pearson's R coefficient nonetheless because it communicates much easier. It has more capabilities for calculations later on as well. So for interval and ratio, what we do for measures of association, we have our Pearson's R. You know about that. We've talked about this before, but it has some requirements and limitations. So first of all, it's only for interval and ratio variables. Second, it assumes homoscedasticity. I'll explain what that is in the next slide. Homoscedasticity. It also assumes a linear relationship, as I've just described. It assumes a straight line. And the advantage here is also that it gives you an exact coefficient. So 1 increase on x is 1 increase on y, if the correlation is 1. Yeah. Spearman's rank correlation that we've just seen for the ordinal variables can also be used for interval and ratio data. This is helpful if we want to see relationships between interval and ratio variables that are not linear, for example, right? Or they are not homoscedastic, as I'll explain in the next slide. So if you think that that might be the case, this is the one to use at first. So what's homoscedasticity? This is easier explained by just showing you how this looks visually. So we have 2 scatter plots on the x-axis and the y-axis. We have some variable, it doesn't really matter right now what we have. But when a relationship is homoscedastic, as you see on the left, it follows this nice sort of sausage shape across the board. So there's no more variation across this imaginary line that we might draw through this scatter plot where dots are further away from it. So the error, so to speak, the measurement error between the line that we're predicting and the dots that you see is the same on average at each point of this distribution of this relationship. When something is heteroscedastic, or not homoscedastic, but heteroscedastic, it looks something, for example, like the one on the right. It's the error, so the distance between each one of the dots and the line that we're drawing through it is going to be much higher on the right-hand side of things than it is on the left-hand side of things. On the left, the line would be minimally different from the observations, whereas on the right, there would be, on average, a pretty high degree of distance between them. So, and homoscedasticity is something that Pearson's R will assume, and the other associations that we looked at doesn't. Spearman's rank correlation, for example, does not. Then linear and nonlinear. I think this is probably clearer, but just in case, here's two images again. On the left, you see a linear relationship. So all the dots, all the observations are on the line that we might predict here. And on the right, you see a nonlinear relationship. So it follows a curve. Yeah, or any other sort of pattern, not necessarily a curve. Then a small note here on outliers. We have two main types that we distinguish, and it's helpful to think about what they will do to your data. We have online outliers. As you see on the left, there's this little dot that's way removed from the rest of the observations here, but it is still on the line. If we would draw a sort of a line that predicts the relationship through all of these dots, that line, that outlier, will still be on the line, right? Would still be on that line. Whereas on the right-hand side, you see an outlier that is off the line. Both of these observations are strange. They should probably not happen. It's most likely a measurement error, but it might also just be a very strange case of something. These two types of outliers have different effects on your on how you are incorrect about saying something about your relationships. When an outlier is online, your main effect will be overstated. So it's emphasized by it. It will reinforce the effect over a longer distance, and therefore kind of make it seem more stronger than it is. When it's offline, it will detract from how strong your effect really is, right? So you see this main group of observations there. The offline outlier will undermine that, right? Because it will somewhat pull the line that we're drawing here towards it. So finally, for looking at relationships between variables, there's also two analyses that I want to address briefly that compare the means of a variable, right? So if you want to see if two groups or three groups or any number of groups are different from one another on one specific variable, there's different tests that you could do. There's a simple t-test, which just compares the mean between groups and tells you, is the difference between those means, those averages, statistically significant? Where the ANOVA does the same thing, it's based on the t-test as well, and it compares the means of more than two groups at the same time. Right? So you see this in this image here. Maybe these are distributions that you'll find in different groups. Maybe these are experimental setups for lab experiments that you're doing, psychology experiments that you're doing. And you want to just see if under the conditions of group 2, observations group 2, or under the conditions of observation group 3 and 1, is there a statistically significant difference? The next section is about multiple regression analysis. This image that you see here is like the images that we've talked about before, where we had a scatter plot in a two-dimensional space, meaning just two variables. We were drawing a line through a scatter plot, through a cloud of dots. What we do with multiple regression analysis is basically adding dimensions to this type of analysis, where this is an example, right? And when there's 3 dimensions, we can still kind of visualize this. But the line then becomes a plane. As you see, what we're doing with multiple regression analysis, when there's 3x or independent variables, we are basically mathematically drawing a plane that best describes all 3 of those dimensions when it comes to the measurements that we have. So this particular image is about the miles per gallon of a car, the weight of the car, and the horsepower of a car. I know nothing about cars, but then this there is a relationship between the weight, the horsepower, and the miles per gallon, how fuel efficient they will be, right? So, and this plane will show that, right? So multiple regression is we try to minimize the distance to the dots and our plane in all dimensions. It becomes increasingly hard to visualize this, of course, as we add more variables. With 2 variables, it's just 2 dimensions, right? So x and y. With 3 dimensions, we can also think about that in kind of the way that we see, right? X, y, z. But if we add a 4th, a 5th, a 6th, a 24th, it will become much more hard to visualize, right? So we tend to rely more on the numbers that we have. Linear regression analysis, the type of regression that we're dealing with, like I said, there's others, but we're looking at linear regression analysis, has a couple of assumptions that limit the data that you can use, or describes how you should transform your data in order to make it useful. So the first assumption here is that relationships, obviously are linear, meaning they follow a straight line between any two sets of variables, between any independent variable and the central dependent variable. There's still just one dependent variable with this type of regression analysis. Secondly, it assumes homoscedasticity for each of these relationships. So we've talked about this in the previous section, where the variable relationship has equal error across the relationship between the two variables. And finally, it assumes interval or ratio data. In other words, what SPSS calls scale. We can cheat on that a little bit, as we've seen in the first lab session, where we looked at what happens when we take correlations, for example, between BMI and the number of years of education, which is scale, or the categories of education, which is ordinal. Right? This was the example in the first lab session. We saw there that for correlation, it gave us a fairly reasonably the same relationship for the ordinal and the scale data, even though correlation, like regression analysis, assumes interval or ratio data, scale data. So sometimes we can cheat a little bit with these assumptions, with this assumption in particular. We shouldn't, but in actual practice, people do this quite often, especially in the social sciences like sociology, political science, and related fields. Okay, so one question that comes up from time to time is how regression analysis and correlation are different and when you would use either. And so there's no real reason to not use both in any given paper that you're writing. So often correlation is used to kind of explore first what relationships between variables look like, and then regression analysis tends to be used as a further analysis to really make one model of the whole thing. So regression analysis assumes a causal relationship. X causes Y, or multiple X's cause one single Y. Where correlation just is looking at, is there a relationship between two things without necessarily being concerned with the direction of that relationship. Regression analysis achieves a formula where Y equals A plus B times X, as we've talked about before. And what we're doing here now with multiple regression analysis, we're adding more variables, and all that really changes is that we're adding more terms, B times X plus B times X plus B times X, to this equation. So each B times X is another B coefficient for any given variable, right? So if the second variable increases by 1, how much does the predicted Y-score increase? Taking into account all of the other variables in this same model. So that whole model as a whole, with all the independent variables taken together, is represented by this one equation with all the B times X plus B times X plus B times X. It still starts at a single A, which is your intercept, your constant, which is where the line starts. And so we use this to predict a value on the dependent variable based on any number of independent variables. This is not technically unlimited, these number of independent variables that you can use, for statistical reasons mostly, but also because our goal with statistics tends to be not to have as big a model as possible, but rather to have a parsimonious model, as this is called. So a model that uses as little information as possible to explain as much as possible. This is the goal with statistics. So here's another example of how we might represent multiple regression analysis in a chart, in a graph here, right? So we've seen this three-dimensional model here. Technically, there's a couple of variables here. In this example, we have body mass index, BMI. We've seen this one before in the lab session, right? And then we have diet score, which I'm assuming is a score for what the diet is like of these people. And then we have age, represented by those big circles, these circles around the crosses there, age over 20 and age under 20. And then we have gender. We have males, females, and again, males, females for each of the two age groups. So if we would take away all of the variables that we're measuring, age and gender, I mean, we wouldn't have these directionals, we would just have the crosses that you see. And if you look at that cloud of crosses, there doesn't seem to be a very clear relationship in it. So if we would just look at body mass index and diet score, there doesn't seem to be a very strong or any relationship between those two variables. However, if we do include age, we see that there's definitely two different groups, right? So people over 20 tend to have a higher body mass index because the circle is higher on the y-axis, and they tend to have a presumably worse diet as well, because it's more to the left than the under 20s. So, and if we wouldn't have included gender here, we wouldn't have gotten these lines through the data there that predict this clear trend upwards, right? So if your diet is better, your BMI will be higher. So actually that should be reversed, right? So the diet score is worse. I'm guessing people under 20 have a worse diet, right? So it doesn't matter. The point here is that no relationship appears to exist when we would have done a correlation between body mass index and diet score, but it does exist if we add age and gender. And this is exactly what multiple regression analysis is good for. So adding more independent variables is what it's used for. And this can be two reasons for it. Well, three technically. So one might be a better theoretical model. So there might be a theory in your field that you're looking at on diet, on disease, on whatever it is. And there might be an overarching theory that somebody in some big thick book came up with, and you want to test that theory. Then you want to measure things that all are part of that theory. So adding more variables in order to fit the theory better. Another reason might be to work from the bottom up in a sense, not technically inductively, but in a sense, right? You're trying to find a model that best explains the data, a better empirical model in other words. So like the example before, BMI and diet score don't have a relationship in this graph. However, when we include age and gender, the empirical model fits better. It explains more of the data that we see. And then finally, we might have multiple regression analysis in order to be able to include control variables. So perhaps there's education as well that we could have included in this graph that you see here. It's not right now, but if we would have included it, maybe that wouldn't have been the focal point for a study, but we would have included it just to make sure that people reading our paper here wouldn't be able to say, well, we didn't look at education, maybe that would have mattered as well, right? Even though it might not have a significant effect in and of itself, we have controlled for it. So to control means, regardless of their education in this example, these effects for male and female, for age, and for diet score still exist when we are trying to explain BMI, regardless of their education level. Just a little warning, doing this stuff, multiple regression analysis, as with the other techniques that we've talked about, is always reliable, because SPSS or whatever program we're using always does the same exact procedure. It does the same calculations. It's blind to what we are doing. It's not always valid. It can be a stupid model. You could just include weird variables to try and explain stuff, so it's not valid. The way it's done is reliable though. It's always the same. We need to talk about a couple of special variables called dummy variables. So dummies are used in regression analysis for specifically interval and ratio variables, sometimes ordinal variables too. Regression analysis is for interval and ratio variables, and sometimes ordinal too if we cheat a bit, as we've discussed before, but sometimes we do need to include normal variables. So one example would be gender that we just saw, but it could be anything, right? Sometimes things are just categories and we want to include them in regression analysis. Regression analysis assumes interval or ratio data, so how do we deal with that? Dummy variables. Dummy variables are very simple variables that can have two values only, 0 or 1. And there can be dummy variables from multiple categories. So, for example, if we had a variable that measures nationality, maybe in your survey you ask people, what's your nationality? Is it number 1 Dutch? Is it number 2 German? Is it number 3 French? People will just select a box, and then the variable will be stored as a nominal variable, right? There's no order to this, Dutch or German or French. It's just different categories, nothing else. It's not like French people are 3 times as much of anything compared to Dutch, or Germans twice as much, or Dutch 1/3 of French. That doesn't make sense. So it's not nominal, it's not ordinal. It is nominal, it's not ordinal, it's not interval, and it's not ratio. So SPSS couldn't put this into your regression analysis. So the way we solve this is by taking this variable apart into 3 variables in this case. So we have 3 categories, and we'll make 3 new variables that just measure, is this person Dutch, yes or no? Is this person German, is the second variable here, yes or no, and French, yes or no. So 3 separate variables. So yes is indicated with a 1, and 0 is indicated, it means a no. And so you could take this to mean how much is this person Dutch, which is kind of a strange way of saying this, or how much of is this person German. It's either 0% or 100%, represented by the 1. Right? There's nothing in between here. And this is what makes dummy variables work, because if we can take it as an extent to which someone is Dutch with only 2 possible values there, then it suddenly becomes a ratio variable. Yes, and this is something that SPSS can deal with. So dummies are special in that way, that you can use them in that way, but you'd have to include them all except for 1. Right? So if you include this in your regression analysis, you would just use those newly created dummy variables and you put them all in. So Dutch, German, and French. Put them all in, and then you'll have to exclude one which will become your reference category. So let's say that you wanted to compare Germans and French to the Dutch, then the Dutch variable is not included, but the German and the French are. And then any effect that you see for the Germans, let's say that Germans are significantly more X or Y than the Dutch, then the Dutch are what you are comparing it to. A second set of special variables are what's called interaction effects. It's really an effect, but when using it in SPSS, you include it as if it is a variable. And what this means is 2 or more variables together may have a particular effect beyond those 2 variables separately. So one example would be if you drink coffee or tea and you like it sweet, you want to add some sugar, of course, to it, but just adding sugar doesn't do much. You need to stir it as well. So the sweetness of the coffee, which if that would be your Y variable, how sweet is my coffee, then there's 2 variables explaining that, sugar and stirring, but they each on their own don't do much. If you just stir your coffee without adding sugar, it doesn't become any sweeter. If you just add sugar without stirring, it might become a little bit sweeter, but not by as much as if you do both sugar and stirring. And so the way you include that into your regression analysis is to create a third variable in addition to sugar and stirring, which is just the value for sugar and stirring multiplied with each other. Yes? You can use dummies in this scenario as well. So, for example, the interaction effect between being German and also being over 50, for example. If you think there's a generational effect, for example, and only for specific nationalities and not other nationalities, you can do this, but it becomes very complex to interpret this. We might be able to get into this in the lab session a little bit. The next section that I'd like to talk about here is about quality control for these types of methods, so for regression analysis, for statistics in general, I suppose. The first is talking a little bit about validity and reliability in measuring. Right? So imagine that you're taking the shotgun, you've seen them in movies and hopefully only in movies, and you're shooting at this target, which you see on the right here. So if we fire the shotgun, a shotgun is a type of gun that shoots multiple bullets, but it kind of just sprays it in one general direction. It's not very precise. So if this target is what we are measuring, and the shotgun is our tool for measuring. So maybe that's a survey question, maybe it's a lab instrument, but that's our tool, our instrument. The results that you see here would be what you might get in different scenarios. So let's start with what we want in the bottom right corner. This is when the gun has shot both reliable and valid. So your measurements, if you're trying to measure something, some latent concept, is measured both reliably and valid. So in other words, it's always measured in the same way and it's measured in the correct way. It is also possible that something is reliable but not valid. So you see that in the bottom left there. All the bullets arrived at the same general location, so it always measures the same thing every time that we do this measurement. So it's reliable, but the measurement is not very valid. It's not measuring what we say it is measuring. Then on the top right we have an unreliable measurement but a valid measurement, where on average we are measuring what we meant to measure, right? The bullseye is in the middle. If we take the average of all those bullet holes, we sort of end up in the middle. So it's in that way it's valid. It is measuring what we say it is measuring, but it's completely unreliable. One measurement might be spot on, another measurement might be way off. So it's not a very reliable instrument. And then top left is worst. That's unreliable and invalid as a measurement tool, where it's neither measuring what we say it is measuring, it's way off, even as an average, but it's also all over the place. So we measure different things every time that we take a measurement. There's some specific types of validity, and you'll see more of these in the book. There's more that are discussed there, but specifically that we can discuss here. We have face validity. In other words, does the thing that we measure, does it measure what it appears to measure? And we have construct validity. Does it measure the theoretical concept or the thing that we want to operationalize? So these are things to keep in mind when you're designing your study, either as a survey, but also as a lab experiment. These are very important things to take into account. What might happen in analyses like multiple regression analysis is a problem called multicollinearity, and I'd like to discuss that a little bit. It refers to how our model relates to the y variable that we're trying to explain. So let's say we are trying to explain this y variable and let the circle represent the variation within that. So some people scored high, some people scored low. Some things are small, some things are big. So whatever it is that's varying, that's represented by the circle. And then we are adding our first variable. This is what we did in Research Methods 1. We just had one variable, an x variable that explains part of y, or correlation works in a similar way, right? So it's just one. And where this x1 overlaps with y, this is what our independent variable explains of the variation in the independent variable. So this relationship is never really perfect. And it also measures things that are outside of our interest, right? x1 relates to other things as well. So let's say that y is exam score, right? To keep things simple, of a group of students. Then x1 might be how much you studied. So how much you studied does explain part of your exam score, but there's other things that impact on your exam score, like how well you slept, how happy you are at that moment in your life. And how well you studied also depends and predicts other things in your life, right? It depends on how motivated you are in general for studying. It depends how disciplined you are, etc. So then multiple regression analysis, we're adding more variables to this. So let's say that x2 here, when we're explaining our exam scores, might be how many hours you slept the night before the exam. So there's some overlap with the studying there, right? Positive or negative. Maybe the more you studied, the less you slept. Could be a negative relationship there. And what they explain of the exam score also partly overlaps. So not all of the explained variance, so as that is called, of the y can be attributed specifically to one of the two. So it's fine if they overlap to a degree. Let's add a third. So we have the third variable here, which let's say that this is how happy you are in general. And so maybe happier people will score better on exams. I don't know if that's true, but let's say that that is true. And that will in turn also affect your sleep quality. It will affect how much you study, etc. So these are interrelated, which is fine. That is always the case. And as a whole, this is your R square. This is kind of a side note, right? The overlap here is called the shared explanation of variance of y between x1 and x3 here. And there's a little bit of x2 in this bracket. The previous model was still fine, but let's say that they overlap more. So maybe your happiness completely overlaps with how much you studied, and it significantly overlaps with how many hours you slept. At this point, the model becomes a little unstable. See, the shared explained variance of y between x1 and x3 is very high here. So they almost explain the same parts of the variation on y, which means that for SPSS, for lack of a more technical explanation, it becomes very hard for SPSS to kind of distinguish, okay, what is part of which x variable. This is what's called a multicollinearity problem. So how can we check for this? The book goes into some detail on how to do this as well. But in SPSS, it's called collinearity diagnostics. So collinearity is when the multicollinearity is too high. There's always some degree of multicollinearity, in most fields at least. But then collinearity would be when the model becomes unstable, and SPSS has some diagnostics for it. I'm not going to go into a whole set of detailed explanations of that, because that would take us too far from the core of this course. But the rules of thumb here are, out of the statistics that you get for the collinearity diagnostics, it'll give you a whole set of tables and charts and things that you don't need to understand right now, but at least we know that the tolerance should be over 0.4 and the VIF should be under 10. We could also do a residual analysis. SPSS will have that option as well. Residuals are the observations that don't fit the model, or at least the extent to which they don't, because typically they wouldn't, right? So in other words, the error between the observations and the line that we're drawing through this. The red lines, as you see in this graph here. We can do a residual analysis where we plot those different errors into a chart, right? So in the line you can't really see the line that we're predicting here, which is good, because this means that the residuals are equally distributed across the relationship that we're looking at. So there's not a real difference across the line. I want to see something like this. This would mean that at the start of the graph here, observations tend to be above what we predict, whereas at the end of the line here we see that observations are actually below what we predict. So this is the problem. This is something that we would have to look into further when this occurs. As a final part of this series, I'd like to talk about factor analysis, which is a specific technique for doing something that is not the same as what we do with regression analysis. Let's get into that. So what is factor analysis? So as sort of an analogy, what we could think of is different musical styles. So let's say classical, jazz, and pop here. This is kind of an older example, so you'll see some pop artists that might not be as happening anymore as they once were. But we have 6 artists at the top there. We have Beethoven, Mozart, Miles Davis, Charlie Parker, Kylie, and Britney. We could add more to this, of course. And what factor analysis essentially does is take a range of information, so in this case these would be musical artists, and classify them into groups based on just the data itself, basically. So it looks at interrelations between variables within the data. So in this case we could simplify these artists into categorizing them as classical, jazz, or pop. And of course there could be numbers there that kind of cross those lines, right? Maybe Kylie at some point made a jazz number. Not that I know, but maybe she did, who knows? In which case Kylie would kind of have a little thin arrow perhaps to jazz as well, right? But we're getting ahead of ourselves a little bit. In essence, factor analysis is a reliable means of simplifying relationships and identifying common components. In other words, factors between groups of variables. So it's reliable, but not always valid, yes? So using factor analysis comes with a whole set of new words and new things to look at, and I'll try to keep it a little simple because this is really taking things a little further into the course, and you might want to look into this further when you do a statistics course later on. But what factor analysis uses as its core is something called eigenvalues, which means how much does this factor, this component, explain in the data. So if you had classical, how much does it explain in the range of musical artists that we have? And with eigenvalues, values above 1 explain more than a single variable. We can look at this eigenvalues in 2 ways. One with numbers, so above 1, and the other with scree plot, which is just a visual representation of eigenvalues. So let's just look at an example and it will become more clear. In the example we'll use some variables in a survey done, I believe, in Korea, South Korea, and where people were asked about their relationship to their work. And they were asked some certain statements and how much they agreed with that. So one is job security is personally important, high income is personally important, opportunity for advancement is personally important, having an interesting job is important, being able to work independently, having the opportunity to help others, having a job that's useful to society, and being able to decide the time of day when one works. So these are different reasons why you might want to choose one job over the other. And we'll use factor analysis to see if we can simplify this. What are sort of the main components? What are the main reasons for people to choose a certain profession without looking at the details of any given? So we've put this into a factor analysis. The way that works is you just go to the menu in SPSS. We can look at that in the lab session if we have time. And throw in all of those variables in a sense, the ones that we saw on the previous slide, and it'll spit out something like this. So this is a list of eigenvalues per component, and the components don't have names because SPSS doesn't know what these things are. It doesn't care or know about anything like this. It doesn't have a brain, it just calculates things, right? So this is up to the researcher to give components a name. So we see that there's two components that have an eigenvalue of over 1, right? So remember, over 1 means that this component, this factor, explains more than any given variable in itself. Yeah, so the component number 1 and number 2 are relevant. We can represent this in a scree plot as well. This was explained to me very weirdly when I took my own statistics classes in my bachelor's, where eigenvalues are on the y-axis and the component number is from left to right. And you see the first two are above 1, right? And the way it was explained to me is it should look like an elbow that you bend. And if you hold your arm up and kind of bend your elbow, where the bend is where you stop caring, which is a very intuitive and weird way of doing statistics, but perhaps it's useful to you someday. Really what's more interesting is to look at the pattern matrix. This is one of the parts of the output that SPSS will give you when you do a factor analysis. The pattern matrix shows you, okay, which variables that you initially gave me are relevant to which of the two components, or 3 or 4 or 5 or 6 components that we have, right? In this case we have 2, and the ones that are circled here are the ones that load significantly, as they call that, to one of the two components. So you see in the left column there's actually the bottom set of variables: personally important, work independently, help other people, job useful to society, and the decided time of work. That's component 1, right? It's in that column. And then on the right we have component 2, where the people say it's important to me to have job security, a high income, and the opportunity for advancement and an interesting job. So the rule of thumb here is anything above 0.44 is relevant. This is based on calculations, on experiments, on literature. It's not based on any intuition necessarily, right? So this is just a rule of thumb. For this type of factor analysis, anything above 0.44 is relevant. So that's the ones that you see circled here. Yeah, and so for the researchers that did this study, there were two components. They gave them a name. One was more sort of the self-development, job security, high income, opportunity for advancement, an interesting job. These are the people that are career-oriented. They are in it for themselves, essentially. The second group, or component 1 here, is to work independently, to help other people, to be useful to society, decide time of work, which is much more about self-development in a more personal way, I guess, in being useful to society, decide your own hours. Money and career is not the main priority here. It's really about having a pleasant life rather, right? So these are different ways of looking at work. And of course, as you can see finally for this slide, the ones that don't load over 44, it's not like they don't matter at all. So for example, an interesting job is mostly part of component 2, but it still has a 0.267 that it scores for component 1. So people who scored high on component 1 in general, still quite a few of them would say an interesting job is important for me, which kind of makes sense with what it is. A little bit about the behind the scenes of factor analysis, just so you have a little bit of vocabulary when you dive into this. It has two main features, which is extraction and rotation. Extraction refers to just finding the factors. In other words, which have the eigenvalues of over 1. And rotation means to simplifying it, to really emphasize the different components that exist in the data. The most common and the default for SPSS for extraction is called principal component analysis. So when in doubt, when exploring this sort of stuff, it's okay to just leave it at the default and see what you get out of the analysis, just to kind of see and understand how SPSS works with this. And the rotation works in this way. So I'm trying to make this a little more intuitive. It becomes a little complex, and we're not going to get into the math of this all. But the default will be unrotated, which might look like this, right? So these numbers, V16, V15, V17, V13, all these Vs, these are your variables in the previous example. So work, satisfaction, all that stuff. And how they load on the factors. So you see that there's factor 1, factor 2, and the dimensions. And they both kind of load on factor 1, right? And in factor 2, clearly one group is loading on one side and the other group is loading on the other side. So if you wanted to make this distinction clear with these dimensions, this is a math operation. This is not cheating necessarily. This is just manipulating the math in order to reveal the effects that exist in the data. So orthogonal rotation would mean that we just rotate the dimensional space to kind of make the two components clearly different from one another. Yeah? We can go more extreme by saying we have oblique rotation, and we kind of abandon the requirement that the axes have to be at a 90-degree angle from one another, to put it sort of intuitively, yeah, which emphasizes the difference between the two factors even more. We see now that one group of variables loads clearly on factor 1, and the other group of variables loads clearly on factor 2. So this is it for the statistics component for Research Methods 2, and as always I'm soothing you out of this lecture part with some weird pictures. Enjoy it while it lasts. This is me during Carnival. Perhaps you'll join us next year. And thank you for watching these clips.